Okay, these are the solutions of the paper 2 style questions on the mechanics review paper. So question number 17 starts by asking the difference between average speed and instantaneous speed. So we need to define the average speed as the total distance divided by the total time. And the instantaneous speed is the rate of change of distance, which is definition of speed, at one instant. A very common mistake here is to say average of speeds, which is definitely not the case. You have to define average speed as such. And then part B, we have a graph. On the next page, we are asked to find the instantaneous speed of the particle at 7.5 seconds. So since we're looking for the instantaneous speed, and we know initially the speed was 0, it's basically going to be equal to the change in speed within 7.5 seconds. So we find that on the graph and then mark that point here where the acceleration is 3 but from 0. Now there's changing acceleration, and we know if we have an AT graph, its area gives the change in velocity. So we're basically going to find the area of this triangle right there, and then using the height and the base, which is 7.5, and divided by 2 because it's a triangle. So we write 3 times 7.5 and then divided by 2. That gives us 11.25 meters. It's always good to also say that we are using the area under graph, because this is a 2-mark question. So awareness of you're using area under graph and the calculation would be the 2 marks. Yes, this is obviously using area, but it doesn't hurt to write it explicitly so you don't miss that mark. And then in this axis, we are going to sketch how the speed varies with time. Now, on a VT graph, the slope means acceleration, and we have increasing acceleration. So this graph needs to have increasing slope. So basically, a curve like this, and that is the 1 mark. All right. Question number 18 is a projectile motion question. We are given the initial horizontal velocity, and we are told that we can use the gravitational acceleration to be 10. So these are the things that I know. I also know the height. First question is asking me, what is the magnitude of the horizontal component of acceleration? We know that there is no air resistance, so this has to be 0. The one and only acceleration of this motion is gravitational, which is downward. Horizontal acceleration is 0. So to sketch the graphs of x component and y component of the velocities, we know the x component is constant, and we know that velocity y component is initially 0, and it increases in the negative direction. Let me try that once again as a straight line. That looks better. So this is 1 mark and that is 1 mark. It's a 2-mark question. Technically, you would still get the mark if you did that, because it only depends on which direction you define as positive. So if you draw it in the positive direction, you would also get that mark. And the next part, we need to find the time taken for the ball to reach the ground. Now we're looking at the vertical motion because that is what limits how much time it can fall for. So we're going to use displacement formula, ut plus 1/2 at squared. And we're obviously using this for y component, where initial y component velocity is 0. We know the displacement is downward 110 meters, and we know that acceleration is downward 9.8. Complete the formula, t squared. When you solve for t, you get 4.7 seconds. So the 2 marks here would be the application of the formula and the answer. To calculate the horizontal distance traveled, we're basically going to use the same formula, but this time for x component, where now the acceleration is going to be 0. So that term disappears. And we know ux is given as 5, and we just found the time to be 4.8. So we basically multiply those two and get 23.4 meters. Now, the path without air is shown, and now we're asked to sketch a path that it would follow if air with resistance were not negligible, which means it was included. Now, this is a 3-mark question, which means there are 3 aspects to this answer. One is less height, the other is less horizontal range, so air resistance would affect both components. And the 3rd mark is showing that it's asymmetrical because horizontal velocity would be also decreasing as the time goes by. So it should really be something like this. So less height, less horizontal range, and by asymmetrical, I mean that this falling part is actually less horizontal distance from the rising part simply because the horizontal velocity is decreasing. Question number 19. We have an inclined plane that a stone block is pulled at constant speed and it's up an incline. And we know the angle, we know the tension. So on the diagram, we are asked to draw and label arrows that represent the forces on the acting block. So obviously we have weight. Always show weight starting from the center of the mass and point downward, so that's the weight. And there's going to be normal force from the base, so that is how you would show it. You can also show the frictional force. We know it is moving up the incline, so you can show frictional force like that. And then calculate the magnitude of the frictional force that acts on the block. Now, for this, we obviously have to separate the 2 components of the weight. So this would be the weight component that is parallel to the plane. And then this would be the vertical component or the perpendicular into the plane. This is weight times cosine theta, and that is weight times sine of theta. So when we calculate, we will find, first of all, we have to realize that this is given at constant speed, which means the forces must be balanced. And using that knowledge, we know every opposite must equal. So on this perpendicular to the plane, the y-axis as we would use for the inclined plane, normal force would be equal to weight cosine theta, because those are equal and those are opposite and they must be equal. Along the plane, we have tension pulling it up, and we have friction and weight sine theta pulling back, which means to have F net equal to 0, I must have opposites equal. So tension must be equal to the sum of weight sine theta and force of friction. Okay, so the rest is plugging in the numbers. For tension, we know this is 4,200. Weight is 15,000. The angle is 12 degrees, which gives us the force of friction. So you calculate this, subtract it from 4,200. We find that the force of friction magnitude or value is about 1,000 newtons. This is a 3-mark question, so to clarify, awareness of the F net being 0, or writing this equation, this would be 1 mark. Substitution and then correct calculation would be 1 mark. Now we are looking at an energy conservation question on a roller coaster track. So it's a ski course. So we have a point A, which is 50 meters above level ground. Point B, which is here. We have a mass of 65 kilograms. Now the question is asking us to calculate the velocity at B. Now you should remember from lessons that this is solved easily by energy conservation. You have to realize that the total energy at any point along a track is constant unless there is energy loss to friction. Well, we do have some loss, so we are given that the 24% of the gravitational potential energy is transferred to kinetic energy. Now, there is a subtle wording here that you need to pay attention to. First of all, the 24% of the gravitational potential energy, let's calculate that. 0.24 times gravitational potential energy is mgh. We are given mass to be 65. We know g would be 9.8. Here's the trick. We have to use 30 meters here because that's 50, that's 20. That difference is 30 meters. And I'm doing that because the question tells me potential energy transferred to kinetic energy. So we have gravitational potential energy due to the 50-meter height with respect to ground at A, but not all of that is being turned into kinetic. At point C, yes. At D, yes, but not at B. At B, there's still some gravitational potential energy due to the 20 meters height. So from A to B, only the potential energy due to the 30-meter difference is transferred to kinetic energy, which is why I calculate this energy value with 30 meters, which gives me 4,586.4 joules. And now I know that is the amount of energy turned into kinetic energy, and I calculate kinetic energy by 1/2 mv squared. So all I'm going to do is to write that with the values that I know. Mass is 65. I don't know VB, but I know this calculation will equal the gain from potential energy, or loss from potential energy, which would be the gain in kinetic energy. So that number would be the value of the kinetic energy. When you solve for VB, you get 11.9, which does calculate to be 12 meters per second square. Actually, I would strongly recommend, if a question like this is now just exam strategy for you. If a question gives you to show a certain number, I always recommend that you write the number as you see on your calculator and then write the 12, because the examiner will want to see that you actually calculated that 12. It was 11.9, and then it is roughly, it can approximate to 12. That is just exam strategy recommendation. Now there's an explain question here of 3 marks. That means we are expected to write an answer of 3 explicit steps. So when the skier reaches point C, 8.2, with a speed of 8.2 meters per second, she stops it after a distance of 24 meters. So there's obviously kinetic energy at C. We can calculate that 1/2 mvc squared, which calculates to that number. This is going to be 0 when it stops, because that energy is used up against friction. So friction is going to steal all of that energy. We know work is calculated by force times the displacement. So all I do is to use that amount of energy which is used up to friction equal to the distance traveled by the force of friction. Dividing that number by 24 gives me the force of friction as 91 newtons. Part C is about momentum. At the side of the course, flexible nets are used. Another skier of 76 kilogram falls normally into the safety net with 9.6. So this is the speed the skier hits the net with, and that mass, and eventually it's obviously going to stop. We're asked to find the impulse. We know impulse is force times the time. So we don't know the force, we don't know the time, but we also know that impulse is equal to the change in momentum, and I do know those numbers, so I can calculate with the mass, and the change in velocity will be 9.6 because it's going to stop eventually, so my answer would be 729.6 kilograms meters per second square. How do you explain this bit? Now, when you think about this motion in your head, you would obviously say, if someone asks you, would it be more safe to stop with a safety net or a rigid barrier? Obviously, it is more safe, but maybe you've never thought about why or how to explain this with physics terminology. So, when you need to explain something like this, first think about what is the same and what the net makes different from the rigid barrier. So you're obviously looking for the difference between the net and the rigid barrier, but you're also looking for what is the same, so you can mention the difference of using the net instead of a rigid barrier. So what is the same? The change in momentum is the same. Even with the rigid barrier or a safety net, you would stop from 9.6 meters per second to 0. But if you use a rigid barrier, if you hit a rigid barrier with that, you would stop, but you would get very seriously hurt. But if you use a safety net, it allows you to stop from that speed in a longer time. And since impulse or change in momentum is equal to force times the change in time, if this is the same, when you increase the time to stop, that means you decrease the force. So when the force is less on you, you get less hurt. And that's how you would explain this question. Okay, definition of the condition of momentum conservation. The total momentum of a system is conserved unless an external force is acting. This second part is crucial in this definition. You have to include that is the condition for momentum conservation. Part BI, once again, we are given a specific law and another specific law, and we're asked to apply how these two how they apply to the condition that we are given. Now, a strategy to answer questions like this. If you're given a law or two, one point will always be mentioning the law. So here I am, force on the ball is equal and opposite to the force on the person. That's Newton's third law. Conservation of momentum, we are asked to apply that as well. What is that? That's the statement right there. So that's my second mark. And then I put it in context, which is here. So that's a strategy you need to learn and build with experience of how to get all of these 3-mark questions, because a lot of the time you think you have answered the question, and you probably have, but you haven't said all the details you should, so you don't get full marks. And then another question here, again, explanation. This time, we are now given the Newton's second law. And the context that the question wants is the horizontal momentum remains constant. So this is what we are meant to state. Well, I just did that right here in terms of the momentum situation. And the context that I am going to explain is that the horizontal momentum is constant. Now, when you apply Newton's second law, yes, this is F equals ma, but it can also be expressed as the rate of change of momentum equals force. Now, that's Newton's second law. That's one point right there. That ticks this box. And then since there is no air resistance, the horizontal force is 0, which means no change in momentum. So we write the law and put it in context. Just a note about this. We learned originally that Newton's second law is mass times acceleration. It is equivalent to saying rate of change of momentum. As a reminder, let me explain why. I write acceleration as change in velocity divided by change in time. Well, if you look at the top, I am multiplying mass times changing velocity. That is change in momentum right there. So I can rewrite this function as delta p over delta t. Dividing anything by t is finding its rate. This is where I'm saying force equals the rate of change of momentum. It's an alternative way to express Newton's second law. In this context, I'm choosing because I'm relating to momentum. Okay, now we're looking at the frictional force. We want to find the frictional force. We know the maximum power output is that number. Mega, as you know, means multiply it by 10 to the power of 6. And we know the force acting. Since it's constant speed, I can use power equals force times that speed. I know the power, 0.75 times 10 to the power of 6 watts. That's going to be equal to force times the speed given, which gives me the force calculating to 17,000 newtons. The last part of this question is a collision between two trucks. So let's draw a picture of this story here. We have a truck X. So this is before collision. Truck X has that mass and it's moving with 4 meters per second just before the collision, where Y is not moving. So this is what happens before. And then as soon as they collide, we are told that they stick together and move off with speed v. So we have to use that information. I can draw a picture. Now they are now sticking together and they are now moving together with speed v. So when it's sticking together combined masses after collision, we can treat them as a total mass moving with a speed v, and that's what we are going to do. So initially vy is 0, initially vx is 4. Finally, they both have v and the total mass of 10 times 10 to the power of 3. When you add these numbers, you would have that mass. So we are going to use the idea of momentum conservation. So I'm going to use total momentum before initial equals total momentum final. You can write this as before and after. So I'm going to look at individually what they have before. I have mass of x, which is 3.7 times 10 to the power of 3, times the velocity of x, which is 4. That's the momentum of x before it collides with y. Momentum of y is 0 before the collision because it's at rest, so velocity is 0. And then after they collide, once they start moving off together, I can now use their combined mass because they are moving together, so they act like one mass of a total of 10 times 10 to the power of 3 kilograms, moving off with a speed v. When you solve this equation, you get 14.8 divided by 10. They both have a factor of 10 to the power of 3 and they will cancel, so I didn't write that. it gives us 1.48 meters per second. To find the kinetic energy lost as a result of the collision, I'm going to highlight what the question wants from us. So it's not just asking a kinetic energy calculation, but it's also looking for the amount of energy that is lost, which means I'm going to need to find the difference between the initial total energy and the final total energy. So basically, I'm going to write 1/2 mv squared. Kinetic energy is 1/2 mv squared. I'm going to write kinetic energy of x and y initially. Well, I'm not going to write the y because it would be 0 initially. This is not moving. And then this is initial before collision. And then this is, oh, sorry, made a mistake. Okay, let's go back. I will write this from the beginning. The kinetic energy of x is not equal. I'm going to find the difference of that from the final kinetic energy, which would be the kinetic energy final. That would be the kinetic energy lost. This is the initial because x is the only one that's moving. This would be their combined mass and their velocity squared. So I'm going to apply 1/2 mv squared for all of the cases. I'm going to write this for x, which has a mass of 3.7 times 10 to the power of 3 times its velocity squared. And then I'm going to subtract the total energy of 1/2. The total mass would be 10 times 10 to the power of 3, so basically 10 to the power of 4. And now I know their velocity. I just calculated 1.48 squared. That calculation gives me 18,648 joules that is lost. If you calculate this bit, I can tell you it's 29,600, and then the final is 10,952, and then you calculate the difference to be as such. The last question on this worksheet, trucks X and Y come to rest after traveling a distance of 40 meters. So now we know that the distance to travel is 40 meters to stop. So we know their final velocity is 0, which means just as in the question we did before, the energy that is lost during this time is the work done by friction. So we have that value right here. Awareness that kinetic energy lost is the work done by friction is actually 1 mark. So I would definitely write that on my paper. Kinetic energy lost would be equal to the work done by friction. This is justifying what you are doing. And if you make a mistake, substitute the wrong number or something, you still get that 1 mark. And then calculation is over here. So basically you can say 1/2. Sorry, it's not this. This is the kinetic energy that they have while they are in the last stage of their movement. So this would be the total mass, and 1.48 squared would be their v squared. And then I set this equal to the force of friction times the distance traveled. When you calculate force of friction, you get 274 newtons. So that would be 1 mark, and then the answer would actually be 1 mark. Now, just to clarify, this question asked for the kinetic energy lost as a result of the collision, not after the collision when they drift away together. This is during the time of impact. The initial energy of the X hitting the Y, and just immediately after they collide, they start moving together, the kinetic energy that they have. So This question, with the number that we find here, is the energy that is uh, lost during the collision at the instant that they collide. This question is after that, what happens after that? They drift away with a common speed of 1.48, and after 40 meters, they are not moving anymore because the energy that they have, which is this, right after the collision, is used up against the frictional force. So I set that equal to force times the distance traveled, and that gives me the frictional force. Thank you.